class. I wanted to come on today and do a quick video about writing trigonometric expressions as algebraic expressions. This was asked a couple weeks ago, but I just kind of got behind with the winter storm, so I do apologize that this is just now coming out. But I am still being easy with due dates and any late penalty, so if you were still confused on this and want to go back after watching this video and try to rework some of those problems, just let me know and I'll be happy to remove any late penalties. Again, I do apologize that this is just now coming out. So, a quick note. The way this problem is worked by your book uses identities. I noticed that on YouTube, a lot of times this problem is commonly worked using right angle trigonometry. You create a triangle and use that kind of thing. Both methods are perfectly valid. That's the way, using right angles is the way I typically teach it. But in this case, I'm going to work at using identities because that's the way your book does it. And I think it's good practice for when we will be confirming and verifying identities in later sections. So that's the way we'll work it. I will accept either method on a quiz or a test. I'm not going to be very picky about that. But that's why maybe there's a bit of a disparity there. Your book doesn't use the right triangles very often. They use them some to establish the basic identities, it seems like, and then we never use them again. So we're going to use the way the book did it. That's okay. Alright, so I want to rewrite sine of the tangent inverse of u as an algebraic expression involving u. So I'm going to start with the inner function. And there's a couple of things that, why is it not writing? Sorry you guys, there it goes. And there are a couple of things that I want you to notice, and that is tangent inverse of u, by definition, equals an angle theta. And also, if we apply the definition of an inverse function, we know then that tangent then of theta must equal u. Okay, so we can see here that if tangent of theta equals u, our goal is going to be to rewrite our expression first in terms of tangent. That way then we can just replace tangent with u, and we will take the trig out of the equation, okay, or the expression in this case. Alright, so something else that might be important is where do my angle theta and this x value of u lie. So since we are looking at tangent, I can just use the domain and range of the tangent inverse function to define that. Okay, so by that note, we have that my angle theta has to be between negative pi halves and pi halves. And this helps when you maybe have multiple answers and you are confused about which answer it is, and that's going to change depending on what quadrant you're in. So this will define where you're at as far as a quadrant goes, which will help you out later on. And then also by the domain of the inverse tangent function, we know that u is negative infinity to infinity. Okay. So my next step, now that we have our information about sine, or about tangent inverse here, my next step is going to be to use this first fact here, that tangent of u equals theta, and I'm going to rewrite that parentheses, what's inside that parentheses, and replace that tangent inverse of u with theta. So sine of tangent inverse u equals just sine of theta. Alright, so this simplifies my original expression. Now it's no longer really a composite function, it's just sine of theta. Okay, so now I mentioned that we are going to use this lovely fact here, that tangent of theta equals u, eventually when we get to the very end. So that means I need to somehow get my sine theta in terms of tangent. And again, this is something maybe that you might be more comfortable with now that we have gone over a couple of sections of identities. And so that's, again, kind of why I like this. This will also help you practice rewriting things, because you do this a lot when you're verifying identities. Okay, so it's a little bit of practice. So a tactic that you will often use, and you have maybe seen this tactic in algebra class, is multiplying your expression by a well-chosen one. Okay, this is some creative use of the ratio of x over x, or something over itself, as 1, and you multiply it, and that allows you, multiply it to your expression, and what that allows you to do is rewrite your expression a little bit, rearrange things without changing the value of your expression. Okay? So my thought bubble here is that I know that tangent, I want tangent. Tangent is my end goal. Okay, I want some things in terms of tangent. But I know that tangent is sine over cosine. Alright, so maybe I need some kind of well-chosen one that involves cosine. Okay? And that's exactly what we're going to do. Let me move my item 3 down just a little bit. Alright, so sine of theta equals sine of theta over 1. So I have not, again, changed the value of my expression. Here I'm just writing it over 1. And then I can multiply that by cosine theta over cosine theta. Okay? Cosine theta over cosine theta. This is a ratio of an expression over itself. So the denominator and the numerator are the same. This equals 1. So when you multiply by 1, you don't change the value of your expression. But in this case, I can use it to rearrange things a little bit. So notice that if I move the cosine over to be in the denominator with sine, I can rewrite this as sine theta over cosine theta times cosine theta rather. Whoop. Well, we're almost there, because now we know that sine theta over cosine equals tangent. Okay, so we get tangent theta times cosine theta. Okay, so now I have to do, now this is probably where you're going to get a little bit, it gets a little bit tricky. Because now I have to somehow deal with this cosine theta. Okay, so I'm going to actually move to the next slide to give us a little more room to work here. Okay. Alright, so again, I have to think. I have a tangent and I have a cosine. What can I do? So the thing that we're going to use is the fact that secant squared theta equals 1 plus tangent squared theta. And this is sort of my thought process here. Okay? Tangent and secant are just two, like sine and cosine, they are always together. Secant and tangent kind of work the same way. And a lot of identities, they sort of play together very nicely. Right? And like cosecant and cosecant and cotangent also kind of go together in a similar way. Alright. My second little thought process here is going to be that cosine is 1 over secant. Okay, so now I'm getting somewhere a little bit, okay? So I can rewrite tangent of theta times cosine of theta as tangent of theta over secant theta. Okay, now I can use the Pythagorean theorem that I have listed here, which is, or the Pythagorean identity, which is secant squared theta equals 1 plus tangent squared theta. Okay? So, we are going to rewrite secant theta. This will allow us to rewrite secant theta in terms of tangent. All right, so we're going to use this now. But notice that I have secant squared. All right, so I have to square root both sides of this identity here in order to get just secant. Okay? So we're going to take that and say the square root of secant squared theta equals the square root of 1 plus tangent squared theta. All right, and what this implies is that I get secant theta. All right, and I can't really do anything with that the right hand side there. Okay, that does not simplify very nicely, so we're just going to leave it as 1 plus or minus 1 secant theta equals plus or minus 1 plus tangent squared theta. Okay, so this is still a quadratic expression here. But remember, whenever you square root a quadratic expression, you get both a positive and negative result. So this is where the quadrant and defining the bounds of our domain and range in part 1 helps us out. So since we have that negative, our theta is between negative pi halves and pi halves, this means that we are in quadrant 1 and quadrant 4. Okay? Just by looking at your unit circle. All right, this means that secant is positive in both quadrant 1 and quadrant 4. So we are just going to use the positive result. Okay? So we don't have to worry about that extra negative. All right? Sometimes this is a subtlety here, and sometimes you can get away with missing it. But if we were perhaps not in quadrant 1 or 4, this would have come back to bite you later. Okay, if you didn't really think about both those positive and negative results. All right, so we are just going to use secant of theta equals the square root of 1 plus tangent squared theta. So that allows us to finally rewrite our expression. Tangent of theta over secant theta, all right, equals tangent of theta. That's going to stay, but I'm going to replace secant theta with the right-hand side of my expression here, 1 plus the square root of 1 plus tan squared theta. Okay. So now I have reached my goal of rewriting our sine theta all in terms of tangent. Okay, and remember, because on the previous slide we said that tangent of theta equals u, now I can simply do one last step and replace those tangent of thetas with u. And now I have again taken the trigonometry fully out of the equation here. All right. So we're just going to write the whole thing. Sine of tangent inverse all right, we said that was equal to sine theta, but then that was equal to tan theta over secant, but then that equals tan theta over root 1 plus tan squared theta. All right, but now we are going to replace this and that with u, because tangent of theta equals u, and that's by definition of the inverse tangent function. All right, so we finally have our last bit of our expression. U equals the square root of 1 plus u squared. And you're done. Again, you could also do this by building a right triangle and use the right triangle identities, seek SOHCAHTOA essentially, but your book hasn't really gone over that. If you are comfortable with it, please feel free to do it that way. I was just kind of working it the way your book does, mainly because we don't do a lot of examples like this, and I thought it was nice to kind of start to see these the concept of rewriting expressions in terms of other trig functions, because that's going to help us again in a more in-depth topic that we'll cover more, which is identities and verifying trig identities. Okay, so let me know if you have any questions on this. Have a great day.